Hello there. My name is Jose Daniel Lopez Barrientos and I will be your instructor for today's session. So, let's get started. This represents the first session of our course on risk theory, and we will delve into the difference between gambling and insuring. So, the topic is called to bet or not to bet. That's the question. This is the overview of our talk. So, first we will start with a simple example on gambling. Then we will introduce a stochastic process, namely the wealth process. Then we will present the calculation of the probability of ruin. And finally, we will get a moral on the duty of the actuarial scientist. Now, to start with, let me ask you guys, how does it sound to you to lose one box every time you do not get doubles on two rolls of a fair die? Now, to get an image of what we are asking here, let me draw in here the outcomes of such an experiment. So in here I will write 1, 2, 3, 4, 5, 6 for the first die or for the first roll of these dice, and I will do the same for the second one. Now, what I'm saying is that every time you get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6, we do not lose one box. That is, just in 6 out of 36 experiments, that is 1/6, we do not lose money. But we lose money every time we get any other result. Now, how does that sound to you? Pretty bad, huh? We use the geometric distribution to model this situation. So, what we are saying is that with this parameterization of the distribution, we can have the amount of money that we will lose until the first double outcome appears. So in here, we can see a depiction of the mass function of this distribution. We use a spreadsheet program to reproduce the mass function we just saw. So in the first column, we just write the support of this random variable, which is the number of dollars we are to lose. And then in the subsequent columns, we write the mass function and the probability distribution of the geometric random variable. So we start off by taking into account the probability of losing just $1, and this is given by this expression, and then we just put this here. Now, from the second row on, we can just copy this expression here, right, like this, and then we can just start accumulating these results, and we will just copy and paste these expressions until we get a 1 in the third column, right? So up to this point we are almost there, right? And there we are with just the first 1 in this expression. Now, with this in mind, we can just ask, in this case Excel, to draw a dispersion graph for these points, and then we can just move our graph to a new sheet where we can put in here the names of the axis. So in here we will put the name of the random variable, that is x, and the name of the probabilities, which is just the probability that x equals little x, and that's it. Now we will implement the technique of the inverse transform to simulate the losses that this experiment leads us to. For that purpose, we will first generate a random number that is a number between 0 and 1. And well, If the number is between 0 and the probability that the accumulated distribution function gives us 0, then the loss will be 0. If the number is between the distribution function in 0 and the distribution function in 1, then the loss will be 1, and so on, right, until the nth outcome. This is an approximation of the graph that we will obtain by this means. In our spreadsheet program, the thing looks more or less like this. So we just count 1, 2, 3, 4, and 5 columns, and we start off writing things right here. So first we write consecutive numbers here. We start off by a 1, and then in here let me just okay, do this like this, yeah, and then put here a random number, and here a realization of the random variable. So in here I will just ask Excel to write a random number, and then I will use the VLOOKUP function, which in Spanish is called buscar v, buscar that set, and then I will have to look for this number in this range. I fix the range, and then I ask the thing to give me a 2 because I wanted to return the number which it finds in the second column of this range, and then I will just content with an approximated coincidence. So in this case I get just 0 because I haven't given it any possible coincidences. So I just copy this range in here and put 0 here. Now, since I just changed the header of the range, I just mark it with another color, right? And there I have it. So now I just will repeat the experiment many times, right? Because the purpose is just to simulate the experiment a huge number of times. So for instance, what I have here is just 498 simulations, and then I have in here almost 1,000, and then I here have almost 2,000, and next I will have here almost 4,000 simulations, and well, I can just do this whole day, huh? So I will just simulate, how about 31,000, okay, maybe like this. So what I have here is many realizations of the simulation, and then in here I will just take the average number of times that I got 0 in my realization column. So in here I put COUNTIF function of in this range how many times fixed, how many times I got this, divided by the number of simulations I just ran. So I have here a number which resembles very much this one here, so I write this and this because these are very similar, and then I just do this, right, and then I have here that this number resembles very much this one, and that this number here resembles very much this one or this one here, and then here we can see a number which is very much like this one. So we can see that all this column is practically the same as E column. I will finish this experiment by asking my spreadsheet program to draw a dispersion graph, right, which is very much like the one we just got in a sheet named Gráfico 1. In here what I have is essentially the same as we had before, and I add some labels, right, and in here I just write the name of the random variable, and in here I just write the probability that x equals little x, and I have it. Now please observe that every time I calculate again, I get just little variations between what I had before and what I have now, right? Now this slide here represents just a summary of what I just did, and well, the computation of the average as we just saw it as just adding up the numbers we just simulated and dividing the sum by the number of simulation is just an invocation of what we call in probability theory weak law of large numbers. That result essentially says that if we have a huge amount of random variables which are independent and identically distributed, right, then the probability that the average of those simulation is away from the real mean goes to zero as the number of random variables that we have increases and increases and increases. Now, the practical implementation of this result is called Monte Carlo simulation technique. Now what I have in here is just the support of the random variable, and here I have the simulated masses. Now with this in mind, I can just ask Excel to give me an approximation of the expectation of these random variables. So for instance in here I can have the expectation, and I can compute this by asking the spreadsheet program to compute this times this. I have 4.99999, that is almost 5, right? So I can just put now the parametric expression for the expectation of the geometric random variable, right? And I can also compute the average of the simulated values we just got. So by calling this function, and I will have almost the same 5, and I can obtain the same result by computing the product between these results here and these other results here. So I have this other form of the expectation, and finally another way of doing it is just by adding the survival function, that is 1 minus this here, and a lot of times until the support of the random variable. Oops. Okay. So I do this by just adding up these elements, and I get the same 5 as I had before. Now suppose that someone asks us, what if you came with a few coins and you could charge for each series of trials? How would you charge? So the question here is, assume that we have this random process, right, which we call the wealth process. This is a Markov process, right, which starts at a certain initial point, which will be our initial wealth, and then we just add a certain level of premium, which in this case is just naturally the expectation of the random variable, that is 5, and we subtract from that sum the amount that we will be required to pay, that is random loss. So we will implement this in our spreadsheet program. So in here we will use this column of consecutive numbers as a column for times. So at the beginning we have just an initial wealth of say $2, and then we just have this 2 plus the premium, which will be by the equivalence principle equal to, for instance, the expectation of that random variable, and then we just subtract the loss we will be required to pay. So in the first case we have this, and then we just continue to find points of this process, and then we just have to draw this graph, which will be a random walk for the wealth process. We will put this in another sheet. That's it. And in here the axis will be denoted time, in this case time, and in this case wealth. Now please note that these numbers are not very good. Why? Because just at the beginning we have things like this here, and then we have things like this here, where we just lose all our money and go beyond just losing it and being very, very, very poor. Now, if we just continue to simulate, right, all those times, we get that the probability of ruin is actually very, very, very large, where ruin means to go below the level of zero money. So it is natural to say yes to this question. Why? Because it is absolutely natural that if we start with an initial wealth of just 2 and we charge just the expectation given by, for instance, the actuarial equivalence principle, then we will get ruined with a very, very, very large probability. Now, the question here is, how large is that probability? So now I will put to the test all the tools that I just presented to compute the probability of ruin by writing here the initial wealth, which will be, for instance, 2, and the premium, which in this case we just set to 1, and then in here I will just compute the probability of ruin, right? And in here I will just put times. So for instance 0, 1, 2, 3, 4, 5 for the next say 10 times, right? This is a horizon of 10, and then in here I will just put the initial wealth, right? And then in here I will just put the previous wealth plus the premium, which in this case is set to 5, and then I will just use the VLOOKUP function. In Spanish I said buscar B, and then I generate a random number, and I will look for this number in the distribution function range for the geometric random variable. I ask it to return the value in the second column, and I return just an approximated coincidence. So what I have here is a value of 7, and that's it. So in this case what I have is just a representation of the wealth process, a realization of this wealth process, and then I here ask if this process is falling into ruin, that is, if we went out of business. So in this case we clearly did, so I just ask if the minimum of all these numbers is lower or equal than 0. In that case we just return a 1, in another case we just return a 0. So I just have to repeat this number of times, sufficient number of times. So what I have here is just a couple of hundreds, then I have 387, and here I have a little bit more, and I can ask if I have some other realizations where I am risking going out of business. So in this case I have 12,000, and here I have a little bit more, and in here I have about 1,000 simulations, no, 100,000 simulations. That's it. And here I have 200,000, and I will just stop at about 400,000 simulations. That's it. And then I just compute the probability of ruin by calculating the average of all these Bernoulli realizations. So in this case, what I have is a large probability of ruin of about 69%, which is actually very much. And then I just have to change these two parameters. Now, by convention, the parameters are written with blue ink, so I can just increase the wealth up to the point of, say, for instance, 5 and a premium of 7. In that case, we have a probability of ruin of say, okay, 30%, which is still very large. So I can just increase the wealth up to a point of 10, and premium, for instance, and okay, where that gets us to. So a probability of ruin of 3%, that's actually very low, but we can just leave it at there, or just increase the amount of money that we had before. Okay, so how about this? With a wealth of just 7 and charging a premium of 12, we can decrease the probability of ruin to 5%. I believe this is actually quite nice, huh? All this being said, allows us to state one of the things that the actuarial scientist is supposed to do. Actuarial scientists are supposed to prevent catastrophes by means of, for instance, the inverse transform technique, the Monte Carlo simulation technique, and the use of random variables, and all this within the context of risk theory. So these are the references, and well, I now just give you my coordinates of contact, so you can contact me in the case that you have any questions. Thank you very much.